This video looks at combinations. Our QCAA subject matter is to understand the notion of a combination as an unordered set of R objects taken from a set of N distinct objects. So I'm going to start, even though we don't cover permutations in maths methods, I'm going to start by talking about permutations and combinations so you can see the difference. So imagine that you have 4 cards, one of each suit, heart, diamond, club, spade, and you select 2 cards in a random order. Now there are 12 possible permutations or arrangements. We could get a heart diamond, a heart spade, a heart club, or we could get a diamond heart, diamond spade, diamond club, etc. So you can see that order matters here. Whether we get a heart first and a diamond second is different to whether we get a diamond first and a heart second. Now that's in contrast with if we're looking at combinations, we don't care about order. So heart diamond is the same as diamond heart. So when we're looking at combinations, there are only 6 different combinations or selections that are possible because order is not important. Okay, now another thing that you can see is there is a difference of 2. There are 2 things that we're selecting and 12 divided by 2 is 6. So there is a difference between our permutations and combinations, but don't get caught up in that in maths methods. So let's look at some examples. Consider choosing 3 letters from A, B, C, D, E. If we were looking at order mattered, okay, we would have 5 things to select first, then we would have 4, then we would have 3. So our total number would be 5 times 4 times 3, which is 60 possibilities. So that's when our order matters. Now combinations, order doesn't matter. The number of combinations is the number of permutations divided by R factorial. So here it's saying 60 divided by 3 factorial. Now 3 factorial is 3 times 2 times 1, which is 6. So this is 60 divided by 6, which is 10. We only have 10 possibilities. So that's getting rid of our repeated arrangements. But as I said, don't get too caught up in permutations in this matter. It's just so you can see the difference between order mattering and order not mattering, okay? So that's the main reason for showing you both. You only need to know combinations though. Okay, so you don't need to know permutations. I'm only showing it so you can see the difference. Now in general, the number of combinations of n objects in groups of size R is what we say is NCR. From n things, we are selecting R. So we're selecting R things from n. So in this case, if we looked at our example, we have 5 letters and we're choosing 3. So that would be 5C3. Okay? The formula is on your formula sheet as well. So don't get stressed about remembering this, and you can do it on your calculator. So you don't need to have to use the formula. The other thing to note is what factorial means. And all that is, if I have 5 factorial, it's 5 times 4 times 3 times 2 times 1. So if I have n factorial, it's n times, take 1 away from n, times, take another 1 away from, and then you keep going until you get down to 3 times 2 times 1. But again, don't stress about the formulas. In all honesty, just think about 5C3 and go to your calculators. So for your calculators, go menu, 5, which is probability, 3 combinations, and put in your N and your R. Okay, and you should, once you do that, see that 5C3 gives you 10, which is what I got before. Okay, so try and do it on your graphics calculator and get that answer. So let's look at some more examples. 4 flavours of ice cream, vanilla, chocolate, strawberry and caramel are available at school canteen. Determine how many different double scoop selections are possible if 2 different flavours must be selected. Now our assumption is that order doesn't matter. I mean, it does for me, because I like my favourite flavour at the bottom, because I like to finish with it, but we're not looking at that. So order doesn't matter. So we have 1, 2, 3, 4. We have 4 flavours, and we're selecting 2. So that means number of possibilities or combinations is going to be 4C2. Go to your calculator and work that out. And you will get 6. So therefore, there are 6 different double scoop selections. Okay, so a team of 3 boys and 3 girls is to be chosen from, so we've got 3 boys, 3 girls, to be selected from 8 boys and 5 girls. Okay, how many teams are possible? So number of teams, because order won't matter, from 8 boys we're selecting 3, and from 5 girls we're selecting 3 as well. Now we need both to occur, so we multiply. That's our multiplication law, which is what we've been doing in probability. When we go across a tree diagram, you multiply. So go to your calculators and work out these. Again, as I said, you don't need to be able to use formula. You can use your calculators to work it out. So that's 56 times 10, which is 560. So therefore, 560 possible teams. Now, selections of any size, when asked to count all the combinations of any size, it'll always be 2 to the power of n. If you want to look at the bottom of page 401 of your textbook, that shows why this is true, but again, that's just an extension. You really just need to be able to find a combination and plug it into your calculator. It doesn't get any more complicated than that. Another example, Nick is making an invitation list for his party and has 7 friends to choose from. If he may choose to invite any number of friends from 1 to all 7, how many possible party lists does he have? Assume he will invite at least 1 person to his party. So this is when you could use that previous rule, or you could just go, okay, well, he's got 7 friends to choose from. He could select 1, okay? Or he could select 2. Now it's or, so we and. Or he could select 3. And that keeps going up to 7. Okay, so that's what that means. So if you go to the previous slide where it says that there, and it does say assume he will invite at least 1 person to his party. So we don't have 7C0 because he's going to invite everyone. So this would be equal to, if we use that formula, 2 to the power of 7, because that's what our n is, but we'd have to take away 7C0 because we don't want that. Okay, so 2 to the power of 7 is 128. 7C0 is 1. We're not saying he's going to invite someone. So that's 127. Or you could just do each one individually. 7C1 plus 7C2 plus 7C3, etc. So therefore, he has 127 possible party lists. Now, applications to probability. 3 students are chosen to represent the class in a debate. If the class consists of 6 boys and 4 girls, calculate the probability that the team will contain exactly 1 girl. Okay, so number 1, we have 6 boys and 4 girls. So we have 10 students. So 10 students in total. So total possibilities We want 3 from that. So no restrictions would be 10C3. Out of those 10 students, I can pick any 3, and that would be 120. But if I want exactly one girl, so one girl would mean that from my 4 girls, I'm going to select 1, but I need another 3 students. So from my 6 boys, I have to select 2. So going to your calculator to work those out, that would be 4 times by 15, which is 60. So we have 60 possibilities of one girl. So our probability of getting one girl would be 60 out of 120, which would be 50%. Okay, so we need at least 2 girls. So we could have 2 girls, which would be from our 4 girls, we're going to select 2. Okay, but that would mean that we'd need 1 boy. So from our 6 boys, we need to select 1. Or we could have 3 girls, because it says at least 2 girls. So from our 4 girls, we're going to select 3, and from our 6 boys, we're not going to select any. Okay, so go to your calculator and work these things out. 4C2 is 6, 6C1 is 6, so that's 36. 4C3 is 4. 6C0 is 1, so that's 4. So we need either of these, so total possibilities is going to be 36 plus 4, which is 40. So it's one or the other, not both, so that's why we add. And our probability, at least 2 girls, is going to be 40 over 120, which is a third, or 33.3%. Okay, complete the exercise.